Hi everybody, welcome back. So this is the second video of this week's lesson on covalent structures. This one is going to discuss three-dimensional structure. Because atoms and molecules do exist in nature in three dimensions, we have to sort of think about them with a little bit different of a view than a simple Lewis diagram, which is something we can draw on paper and get a pretty good sense of what the molecule kind of looks like and how the atoms are arranged against each other. But it is not a true representation of what the atom or molecule looks like in nature. So to understand three-dimensional structure, you have to understand a theory known as the valence shell electron pair repulsion theory, which in itself is kind of a mouthful. So oftentimes it is abbreviated or acronymed out to VSEPR, or sometimes even people say VSEPR theory. And so as the name does imply, the idea here is that the electron pairs in the outer energy level or valence shell of atoms repel each other. Negative charges repel other negative charges. And therefore, atoms surrounding a central atom in a simple covalent molecule will try to repel each other as much as they possibly can, and therefore they stay as far away from each other as possible. And that, depending on how many of those surrounding atoms there are and how many lone pairs there are, we can start to figure out the geometric shape of a variety of molecules. And there's a whole bunch of these shapes out there. For the standard level IB chemistry curriculum, you are required to know the shapes that come with at most 4 regions around the central atom. So that essentially means that any atom that breaks the octet rule by allowing 5 bonds or sometimes 6 bonds is not a required part of this course. So you'll see in this slide here that we're looking at together, there are a couple of shapes, the bottom two, trigonal, bipyramidal, and octahedral, that the central atom represented there has more than a full valence shell, more than 8 electrons. So those are actually interesting shapes to look at. And there's resources in this PowerPoint that you can use to examine them. But I will be focusing on the first 3 shapes: linear, planar, triangular, and tetrahedral, because those represent what's more typical of atoms that don't break the octet rule. So let's take a look at it together. So what we have to keep in mind is this theory is all about electron repulsion. And repulsion happens in both bonding electrons and non-bonding electrons, because whether they're attaching 2 atoms together, or they're just a pair of electrons hanging on an outer atom, they're all negatively charged, so they all repel each other. Double and triple bonds here have a very limited effect on the shape. They are oriented together, so they're very close. So that actually means that they behave in terms of repulsion as a single unit. We often call these units steric centers or electron regions. And that can help to clarify, because sometimes when you're talking about bonds and sometimes you're talking about lone pairs, it can be kind of confusing. So you'll hear me refer to the areas where electrons are around a central atom as steric centers, rather than calling some of them bonding regions and some of them non-bonding regions, or calling some of them lone pairs and calling some of them bonds, because there's also triple bonds and double bonds. We'll just clarify by calling them steric centers. So we often want to pay attention, once we've drawn a molecule in 2 dimensions, how many steric centers they have, how many bonds, how many lone pairs, add them all up. You want to know that total number. And then the non-bonding ones are important to pay attention to as well, because non-bonding electrons have a higher concentration of charge. It's not distributed out between 2 atoms. They tend to be more repelling than bonding electrons are. So they cause us more repulsion, which makes the angles in the 3-dimensional structure a little bigger than they would be if they were bonding electrons. So kind of so far, the big theme is first draw a correct Lewis structure. Once you've done that, then count the steric centers, count the regions around the central atom, figure out how many there are. Each number of steric centers is associated with a particular kind of geometric shape, which we'll go through together in a minute here. And then decide whether your structure has non-bonding electrons. And each of the basic shapes that we'll talk about has sort of a modified version of it if one of the steric centers or more than one of the steric centers is a non-bonding pair. That actually kind of slightly modifies the shape. So there'll be some exceptions or kind of like modifications to the general process that we'll be looking at together. All right, so let's continue on. In general, this idea of repelling electrons kind of goes bonding pair to bonding pair is the least amount of repulsion because the negative attractive force is kind of limited by the bonding between the two atoms that are connected by it. So they're the least repelling. But when you have a bonding pair next to a lone pair, that repulsion increases some, but it's the maximum repulsion when you have a lone pair next to another lone pair. Those kinds of things really maximize the distance between them, repel a lot, and modify the shape to a large degree. Just as a reminder here, what we're looking at is the regions around the central atom only. A lot of times I notice students make a mistake and they're looking at the lone pairs of atoms around the surrounding atoms, but it's not about those. It's only about the central atom. So make sure you're focused on the central atom and what kind of things it has around it. So take a look in here. These are 3 different molecules that have some similarities to them, but based on their amount of non-bonding versus bonding pairs, their shapes kind of modify and the angles that are associated with their geometric shape change as well. We can see at the top the molecule methane, which is CH4, has no non-bonded pair of electrons. It strictly has bonding pairs. And the angle between the bonds of all of the hydrogens, it's only emphasizing one here, but those bonds are the same all the way across. Those angles are 109.5 degrees. Ammonia also has 4 steric centers, which you can tell by looking at the central atom has 1, 2, 3, 4 regions around it. 3 of those regions are bonds to hydrogen, and 1 of the regions is a lone pair. You can see here that the angles are smaller for ammonia than they were for methane. And that's because that non-bonding region has a greater repelling effect than the bonds do. So it's sort of like that lone pair is pushing on the bonds and squeezing them closer together, making that angle slightly lower, about 107 degrees rather than about 109.5. And then finally, we have water. Water has 2 lone pairs and 2 bonds. And remember that the lone pairs repel each other even more than they repel the bonding pairs. So we have an even further squeezed angle in water. The angle ends up being 104.5 approximately, rather than 107 or 109. And again, you can see that it's still got a sort of a same steric center structure. There's 1, 2, 3, 4 steric centers in all 3 of these examples, with a slightly modified angle because of the presence of the non-bonding pairs. So you can see that those non-bonding pairs have a pretty significant effect. So we're going to start to now name the different shapes that come about depending on the number of steric centers and the number of non-bonding pairs of electrons within each steric center. So the shapes are based on the geometry of atoms. So it's affected by the arrangement of all the valence electrons, including bonding and non-bonding. So you're going to see a different name for each of the 4 possible steric centers, and then also modifications of that shape based on the presence of non-bonding pairs. So we'll kind of go through them one at a time in order. The first shape that you're going to come across is a simple one called a linear shape. Linear shapes occur when the central atom has 2 steric centers around it. Like in this example, central atom X is bonded to 2 atoms Y. In that situation where there's only 2 steric centers, the way that they get the farthest away from each other is by being in a nice straight line. On one end, there's one set of electrons, and one end, there's another. It can't be any farther away from each other. So that's what a linear molecule looks like. And in a linear molecule, the bond angle is relatively easy to predict. Obviously, it's about 180 degrees because it represents a pretty straight line. So the things that you'll want to be able to do with the VSEPR theory is describe, number 1, the shape, but number 2, the bond angle as well. So it helps to have a little bit of geometric background knowledge. I will also be sharing with you a chart of the shapes and bond angles that go with them so that you can use that as a study tool. Some students just memorize the shapes and bond angles. You don't always have to do that if you have a pretty good sense of what the 3-dimensional shape kind of looks like, but it might be a helpful tool if you need it. So that is the linear shape with 2 steric centers. Let's move on to 3. So if a molecule has 3 steric centers, central atom X surrounded by 3 Ys, then it's going to be essentially something called a triangular planar, or sometimes called a trigonal planar molecule, because the way that those atoms take up the least amount of or get as far away from each other as possible is by spreading out into a flat plane. So it's a plane with 3 sides to it. And because the plane can be represented sort of like by a flat circle, you can divide it into 3 parts and then decide that the bond angle is exactly 120 degrees. There's also a modified shape that comes with this one. If it ends up that one of the 3 regions is a lone pair rather than a bond, because the lone pair repels further, then the bond angle shrinks a little bit. It becomes a little less than 120. Sort of a general guideline is if you have a presence of a lone pair, each lone pair decreases the bond angle by roughly 3 degrees. That's an approximation. It's not a mathematical calculation, but if you're taking a test and you need to figure out a bond angle for something with a lone pair in it, it can be just a really simple way to make an accurate guess. So I would say the angle for this V-shaped molecule is roughly 117 because the lone pair will shrink that angle by about 3 degrees. The shape itself is a little different with a lone pair. It's known as V-shaped, and it kind of looks like a V. You can kind of see it. This shape also has some other names. Some people call them bent. Some people also call them angular. So you can use any of the 3 descriptors for that shape, but with 3 bonds, it's called trigonal or triangular planar, and with a lone pair present, it modifies to a V-shaped or bent structure. When there are 4 regions around the central atom, 4 steric centers, the shape is called tetrahedral because it makes a 3-dimensional tetrahedron. So you can kind of see here, generically, central atom X will have 4 Y atoms surrounding it. The little notation that you're seeing here is maybe helpful to think about a drawing in 3 dimensions. Each line is in the same plane, and then this little dash part of the notation is intended for you to think that it's going back, like into the computer screen behind the central X atom. And then the wedge that's bold is intended for you to imagine that it's coming out at you. It's coming out of the screen in front of the X. Again, tricky when you're looking at 3-dimensional things in a 2-dimensional format. Sometimes you have to have little notations to help you do it. So back to the tetrahedral shape. If all 4 regions of the central atom are bonds, not lone pairs at all, then it is a strictly tetrahedral molecule, and all of those angles are the same, and they end up being 109.5 degrees. This is not 360 degrees divided by 4. Because of the way that the tetrahedron works, it's not a complete circle. So this is one of the angles that is often just good to memorize. With some trigonometry and some detailed plotting on an X, Y, Z coordinate plane, you can actually prove the angle of 109.5 degrees, but the proving of it is not required here. So I often ask students just to memorize that bond angle of 109.5 for tetrahedral molecules. The other 2 shapes you see here are modifications of tetrahedral that occur when 1 or 2 of those steric centers become lone pairs. In the second image here, 1 of the 4 steric centers is a lone pair and 3 remain. So you can sort of see the modification of shape. The 3 remaining bonds press downward because of the repelling force of the lone pair, and the lone pair kind of sits on top of the molecule. This makes the structure look more like a pyramid, which is why it's called a pyramidal shape to it. And the angle itself shrinks as well because of that pushing of the lone pair. You can actually see it decrease by about 3 degrees. So we usually assume that this one is roughly 107 degrees, maybe a little bit more like 106.5, but roughly 107 is usually what we describe. And then in the V-shaped molecule that you see here, it looks on the outside very similar to the same kind of shape that you would see in the 3 steric center version with 1 lone pair. It's also bent or V-shaped, but the angle's a little bit different. Because of the presence of two lone pairs, it squeezes that angle a little bit closer, and it's even smaller.